Okay, so welcome everyone to another LIP seminar. And today we have the pleasure to have Raghav Elayavalli with us. So, Raghav is currently an assistant professor at at Vanderbilt University in Nashville, but their career started at Cornell College in Iowa, then doing the master's studies at Stony Brook, and finally the PhD in Rutgers in New Jersey with a thesis on jetting through the primordial universe in 2017. So primary research from Raghav has been always around heavy collisions, mainly on jets and jet substructures. But after the PhD in CMS, Raghav joined actually for a joint position between Yale and Vanderbilt University, Yale and Yale University, under Star Trend at RHIC, where Raghav was convener of the jet physics working group. Currently, Raghav is back to the CMS collaboration, but is also a member of the EPTIC detector for the EIC to be developed in the US. So today, Raghav will present us an unexpected journey on jet substructure. So please go ahead. You have 50 minutes.
Great. Okay, thank you very much, Liliana, for the very kind invitation. I have absolutely enjoyed my time here in Lisbon. First time outside of the Lisbon airport. I always stop in Lisbon when I go through to Geneva in the past. But yeah, super exciting. So for people who get this reference, a very wise man once said that it's a dangerous journey stepping out of your door. You never know what you may find, and the world is out there, right? So the idea of my talk is essentially what jet substructure evolved as, right? Where did we start? Going from the LHC to RHIC to EIC. Is it possible to maybe swap the lights? Yes. Off this and on that one. Yeah. Perfect. Yeah. Yes. Thank you. So here you can see out of the back end door, there is an event display from Atlas. This is actually a Higgs to BB bar. Okay, so both BB bars are tagged as a dijet. Is actually a very large jet, but subjets inside are tagged as Bs. That is where substructure started. And then we're going to see essentially where we go from the LHC to RHIC to the EIC. So this is the story I'm going to tell you today is mostly about what we are currently thinking about on the other side of the pond, right? What is the plan for long-term physics in the US, particularly in the jets and nuclear side? So there's going to be 3 topics today. So I see there are a lot of students here, so we will try to keep it at this place where you can understand. We're going to deal with introduction, motivation first, and then talk about how can we complete the RHIC mission? What is the physics we're going to do until its conclusion? And the longer term goal is in the US is the EIC, the Electron-Ion Collider, that is going to probe discovery physics about fundamental QCD and also about non-perturbative part of the QCD machine and more about hadronization. I am contractually obligated to say every 6 words, one of them has to be EIC. So we will try to make sure that works. And if I miss it, don't report back to Vanderbilt. So let's start with where we are now, right? So very simple questions. What are jets? So you go to CERN, you ask a theorist like Liliana what jets are. She will tell you that, well, there's a parton shower starting from a quark or gluon. She can calculate it using Dirac splitting functions and some resummation thrown in there to make sure that they're all confined in a certain angular space. And then she does some magic with non-perturbative corrections and gets a jet, right? So jets are not something very new. Jets have been seen since 1979. So this is the event display from TASO. This is the famous Mercedes event that showed the discovery of the gluon. So you have a quark going out this way, a quark and a radiated gluon. You can ask which jet is the gluon. And when this was announced at the DAISY, the journalist actually asked this question. Physicists had no idea. Again, tells you, since then, we have been doing lots and lots of work to tag a jet as a quark or a gluon. Just goes to show how important journalism is, and that carries now, right? This is the event display from 1991 from the Opal collaboration, very high energy quark anti-quark pair production, right? And you can see a kind of structure of a jet that becomes very similar to you, right? You kind of think of what a jet is without even knowing what a jet is, right? You ask an experimentalist like myself, we have our collider event, we get a stream of particles. We can essentially say that they are more or less collimated because of high energy. We are talking about relativistic particles, so Lorentz boosting means you reduce the angle, right? We run some procedure that we call clustering, which starts with finding particles close to each other by some metric. Doesn't matter what it is. You define some criteria, and then you start grouping particles. You group them, you get this kind of prong structure, and then you continue this recursively until you're left with no more particles, and the only things you're left with is a jet. This is what we call a clustering tree. So the information content in a jet is effectively the full momentum of all the particles that you have. Once I tell you all the particles that produce the jet, you can calculate anything you want to know using that information. It's very hard to measure the full momentum in an experiment because it's hard to measure the particle's mass, the species. You have calorimeters, they are notoriously weak in the energy resolution. If you have a trackers, well, high momentum, they bend in the magnetic field. They don't bend as much, so the curve fitting breaks, the momentum resolution fails. So utilizing the clustering information when particles are grouped together is a new dimension on top of the full momentum. That is where we are going to focus on our talk today, right? So why does this procedure work? Why do we think clustering works? So I'm showing you here, think of it as a ratio. What I measure in data divided by what Liliana calculates in theory, right? So that's the y-axis. Basically, each solid line here, think of it as 1. It is scaled by some number to make the plot look fancy, but otherwise, it's more or less 1. And the data points, the points here, are different measurements at different collision energies. The x-axis is the transverse momentum of your jet. Why do we look at transverse momentum? Because beams are coming in z-axis. Anything that is produced goes in the transverse direction. Initial momentum in the transverse direction is more or less 0, barring some intrinsic kV, don't forget that, right? So any final momentum in the transverse direction is produced in the collision. That's what we want to study, right? So you have 3 orders of magnitude in transverse momentum. You have several different orders of magnitude of the collision energy, and each of these spectra is actually a steeply falling function. So overall, this is very good. Right? Across different orders of magnitude, different jets, each of these points here correspond to a different experiment, different groups of people. So it doesn't matter who does it, as long as you follow a prescription of what a jet is, and your theorist also follows that, you end up at the same place. You can use a jet as a proxy for a hard scattered particle. Okay? So that's the first step. If this didn't work, I will probably have back somewhere. Right? Good. So that's all in vacuum. Jets and the QGP, there's a very nice story, right? So let's say we are doing some heavy ion collisions. These are spherical nuclei that are accelerated and they are Lorentz contracted along the direction of the motion. So back to your classical mechanics. They are essentially becoming pancakes. At the time of the collision, let's start our stop clock, 0 Fermi over C. The jets are essentially hard scattering in this case, so they are produced near instantaneous because it's essentially 1 over the energy scale squared, right? So 2 jets are produced because we need at least 2 back-to-back to make sure our momentum is conserved, right? And they essentially evolve along with your plasma. The key word here is concurrent evolution. Jets evolve, plasma evolve, and they talk to each other. Why? Because the jet is a color object, quarks and gluons evolving. This is a quark gluon plasma, so it has quarks and gluons. And they interact via the strong force. They can motivate the jet to lose a gluon, to radiate a gluon at wide angle. They can break color coherence. There's a lot of work done in Lisbon over the many years, and also Santiago, this very big community that essentially trying to study this from the theoretical side, right? So jets are produced early, they traverse the entire lifetime. So that is a very nice story to be told here, right? We can learn something. So let's think of how to quantify a story, right? So for this, we have to go back even further. Let's go back to Aristotle and ask, what is a good story, right? The first thing you need is something called harmatia. So forget my Greek pronunciation, that's important, right? So this is, you need a main character, and you need something that is unique to that, something that is almost tragic, right? Something makes you want to root for the main character, or essentially hate them at first, and then you learn more about them, right? Jets are, of course, our main character. They are the hero of our story, right? They are color-charged quarks and gluons, and during their evolution, it is a probabilistic thing. You can never tell this is what a jet structure looks like for a given jet. It's always a probabilistic thing. When you measure it, you don't know what you're going to get a priori. You get a distribution, right? So there's a phrasing that I really like, is that different jets are different, right? You actually, in Lisbon, you are actually very familiar with this if you read or know about your famous literature, is you can go to Fernando Pessoa, yeah, who has several different heteronymous, right? These are people he writes as, right? They have very different characteristics, they have very different behavior, and essentially think of them as going through the plasma. They experience it in a very different fashion, right? So this is a pretty famous plot from the nuclear physics long-range plan in the US, which is a kind of a long-term document, right? So this is the temperature on the x-axis of the plasma. This is the y-axis is sort of a resolution scale, so it's a kind of a distance metric. Each of these lines correspond to a different type of jet, depending on its topology, right? So different jets, they go through the plasma, they see different parts of the plasma. How do they do that, right? That's where we get to the second part of our story, right? This is the eureka moment. This is where you finally get what the story is about, right? You know that the modification of your jet, as they go through the plasma, something happens to your jet. They radiate more, their structure changes, right? Such as it's, you can measure its momentum, you can measure the yield, you can measure the fragmentation function, and these things turn out to be modified in the plasma, right? And then you can do an inference. You can say, because the modification happens as it goes through the plasma, it tells me something about the transport properties of the plasma, right? If I want to know about the viscosity of water, right, I would probably time my graduate student at Vanderbilt, ask them to run in water, and then put them in the swimming pool and ask them to run at the same speed. They will probably take a much longer time. From that, I can infer what the viscosity, the drag, the experience. They'll probably have less fun than me doing the experiment, right? So this is where we can also go back one more step. This is a systematic method of study, right? This goes back to the beginning of scientific inquiry in the Portuguese language by Luis Antonio Bernet, that says this metodo estudar, which is essentially how to study, right? So there is a way in which we need to do this measurement, right? We have to first know what the jets look like in order to know how they're modified, right? Because if I only measure the speed that the student is running in water, I don't know what they could have done in vacuum. There is a method to this madness, right? So that's where we get to the last part of the story, right? Which is peripetia, or everything's changed. There is a reversal. What turns out to be the bad quantity of the hero is actually a good quality, and we can learn something about this, right? So the realization that jet quenching is dependent on the topology of a jet, right? So if a jet has a very wide emission, that will see the plasma differently than if a jet is a very narrow jet. If it has a different substructure, I haven't defined what it is yet, but if it has a different topology or substructure, it may experience quenching differently, right? And that's where we get to the second, the last part of the statement is that different jets are quenched differently, right? So that is effectively the plan of studying experimentally this method of energy loss. Is you can study the microscopic properties of the plasma at varying scales, at varying length scales, right? Think of it like you can essentially have a jet that is a very, very, very small resolution. It can see if your plasma is consisting of maybe a pair of quark charges, or is it maybe a quasi-particle structure, or is it a pure fluid-like structure, right? And that's where I said the last part, it's inherently two steps. You cannot do step 2 without doing step 1. We have been doing step 2 for a long time without doing step 1 in heavy ion collision. I mean, this is a fact, right? The last 2 decades of measuring heavy ion in jets, we have really not quantified what the vacuum jets are like. This is a new thing. We are learning it now, and that's where I'm going to take you to what jets look like in vacuum first, right? That's where we get to our origin story of jet substructure. So this is a sort of a biased view, okay? You can go to Lund and you can ask Leif Lundblad, or you can ask Torbjörn, and they will tell you they've been doing substructures in 1984, which is true. They have been doing this, but what we have actually measured from substructure essentially kind of starts in the last decade by Jesse Fowler and collaborators at the MIT, where effectively they quantified a metric using particles inside the jet to say this substructure looks different than that substructure, right? Take, for example, here a boosted hadronic top decay versus a standard quark or gluon jet, right? This top will decay to a W and a B, the W also decays hadronically. So you will get 3-prong structure, right? In some metric, however you define it, right? Here you have 3 prongs, here you have more or less 1 wide prong, right? So that is the difference to identify your signal, which is a boosted top. And the idea was that maybe supersymmetry will go into this stop, which is the partner of the top, or you have some boosted vector boson like a Z prime or one of those things, right? So you can differentiate that signal from your background. So I am a fundamental QCD person. I have no idea what beyond the standard model. What they call background, that is my signal. I want to know how these quarks and gluons essentially evolve. Every time we draw this cartoon picture sticks in my head. I showed you in the beginning, there is a natural timeline along my slides, right? Each figure starts with the parton, there is a shower, there is hadronization. That is what I want to learn, right? So what is substructure, right? Substructure is just some physics-motivated combination of objects inside your jet, right? They can either be particle distribution, so individual tracks, you can combine it maybe to give a jet mass, which is the 4-momentum norm, or you can look at the fragmentation function, you can look at jet shapes, how wide they are, right? Or you can go to maybe do some algorithmic fanciness, right? Like our expert here, Liliana, does using subjets or using a different kind of reclustering algorithm, right? You can either do reclustering or declustering, walk backwards through your clustering step. So in principle, the right-hand side has one more extra dimension of information, as I said in the beginning, right? Because it uses how things are clustered. So what do I want to study in this is essentially both sides of the QCD regime. I want to do fundamental QCD. I want to look at its evolution. I want to look at its both non-perturbative structure and perturbative structure, right? This parton shower I took this from Pitya. It's an example of a gluon splitting into different gluons, right? This is unmeasurable. We're talking about partons. We don't see partons, right? We see hadrons. We have to reconstruct them to give us this structure, right? We need something that translates this intrinsic, unmeasurable physics that is exciting into something that is robust experimentally, not sensitive to background or detector effects. You do unfolding, you do the correction. We'll talk about it later on, and extract this dynamics. By the way, if you have questions, feel free to ask in the middle. We can stop anywhere. So how do we access the splitting kinematics? So now we can actually go back to Lake and say, okay, we are sorry, we didn't listen to you before. Can you tell us something now about how to look at the substructure? And then Leif says, well, we have been doing this thing called Lund planes since 1993 or something, right? So then everyone remembers there's something called Lund planes. What they are very simple. So here's the structure I have, right, of a jet that radiates a gluon here, maybe another gluon there. So there are 3 subsequent radiations. Ignore the other branches here. At the first radiation, I have an opening angle and I have a KT. A KT is basically the splitting scale, right? It's the Z, which is the momentum fraction, the PT of the parent. So effectively, it's the energy of a softer particle times the angle, right? In some units. So now you can say that is my y-axis, that is log KT. There's a reason why we do log, because the splitting is proportional to 1 over theta d theta, 1 over z omega z theta d z theta. So when you integrate it, you get logs. This is QCD. There are always logs everywhere. When in doubt in an exam, just put a log in front and you will probably get some credit, right? So at each splitting, you have a value of the KT and you have a value of the angle. So this is log 1 over theta, which means smaller values here is large angle. So 1 over is just the inverse. So that's the first emission. The second green one happens somewhere here. The blue one happens somewhere there. In QCD, we expect angular ordering. So subsequent emissions are narrower than the previous emission, right? So that's why a single jet has a pathway somewhere like that. So if you do this for multiple jets and you fill in this phase space, you can extract different regions of physics from this phase space, right? You can say there's a hard collinear radiation is somewhere along this direction. Soft large angle radiation is over here. There's some, if you go lower in KT, you get non-perturbative physics, you get hadronization effects, right? So that is the Lund plane. That's what people are now starting to measure across experiments. So I'm going to give you one example from the EIC experiment, right? So this is, they did the fully unfolded measurement of the Lund plane, and they are now slicing and dicing. Right? They are going to plot the log KT for a given range of log delta R or delta R between 0.1 and 0.4. So effectively, they take this Lund plane, they slice it, and then do the projection on the KT. Right? So the data is in the black markers. This is still proton-proton collision. Right? The data are in the black markers. Ignore this. There's too much. Alice always does this. There's more text than points here. Just look at the bottom panel. Right? That is way more interesting. All you need to know is that there is a significant trend between all the different Monte Carlos and your data, right? And the trend happens in different regions. So log KT in this place is where we expect more perturbative physics, because let's say 1 GeV is more or less the difference between perturbative and non-perturbative physics. That's why log KT is useful, because log of 1 is 0. Right? So somewhere around here is your transition regime. Somewhere over here is the non-perturbative sector, and here you have a perturbative sector. Right? So across this regime, you see that there are some Monte Carlo models like the Sherpa with a different model, or Pythia or Herwig, whatever. They're details. This is for Lake and Simone from Herwig to say, oh my God, there's something we need to do now, right? This data actually tells them where this is, what phase space this is happening. But we're not done here, right? Because the Lund plane, as exciting as it is it is an integration over all the splits. The key question, it doesn't tell you when this difference happens. It tells you where in the phase space it happens. It doesn't tell you when along the jet shower do these differences pop up, right? So that's why, as a theoretical concept, I like the balloon plane. I don't think it's very useful as a measurement per se. I think making something like this is all the more useful. So that is supposed to be a red color, and this projector doesn't like red color. So we'll get there. So the previous slide was about the LHC, right? So now we're going to RHIC. So we are actually following along my career path. So we started as the LHC, we go back to the RHIC, right? It's a much lower energy. The center of mass energy is 200 GeV, right? So when you say something of jets, your jets are typically on the order of something like 10 to 40 GeV. It's a significantly steeper spectrum. Here you can have a preliminary measurement from the Phoenix collaboration of the ZG. The ZG is basically this B here. It's the momentum fraction at a given split, right? And it's bounded between 0.1 and 0.5. So 0.1 means that the ZG is very asymmetric. So the splitting, the parent splits into a significantly softer proton, right? ZG of 0.5 means that they are exactly half-half. You have a democratic splitting, right? So here you have a dictatorial jet, here you have a democratic jet. So these are two different data sets, and from Phoenix, you can see that there is more or less this kind of falling shape for 10 to 15 GeV. It matches very nicely with their Monte Carlo. This is again a narrow jet, so R equals 0.3. Let's go to a bigger jet. So this is what I did in STAR. R equals 0.6 is wider, and the PT is roughly a factor of 2 different. So we increase the size, we also increase the PT, right? And this one has this perfect 1/Z picture that you get from your D-glass shape. For reference here, this gray shaded band in the back is actually not an uncertainty, it's a theoretical calculation, right? This is by Kunnawalkam, Felix Rigger, Tai Li, and others, where they essentially do jet functions to calculate what is the splitting inside the jet, right? And this light shaded region is actually data uncertainty. So now we are at a point in jets at RHIC where theoretical uncertainty is the one that is dominant, right? You have to vary your factorization scale. You have to vary your renormalization scale, right? When you do that, you're talking about a 30 GeV jet. The angle of the jet is roughly 0.6. That's the radius, but there is a significant variation in it. Let's say the angle is something like 0.4, right? So this effective scale in the process is a PT times the radius. So 30 times 0.4 is more or less 1.2. So you're getting very close to your non-perturbative sector. Any variation you do in your theory blows up. But I'm not satisfied with this. This is great. I want to go to a place and do a measurement where theory cannot even come close at this moment, right? So that's where we did next. So instead of looking at the Lund plane, which is integrated over all the splits, I asked, what is this DG distribution for the first, second, and third split? So subsequently, you remember this cartoon. So the red, the green, the blue, that's the first, second, and third. Okay, as an experimentalist, my color theme doesn't match. So I'm being normal, right? It's okay. The black one here is the first split. And you can see the first split in your emission, very nice, is 1/Z. You can ask what is the corresponding opening angle of that first split. It's more or less a broad distribution, more or less wide angles, right? So go back to your QCD class, you have soft wide angle radiation. So that checks out, right? So if you go to your second split, you're no longer 1/Z, you're kind of becoming flatter. You go to your third split, you're completely flat. This flat distribution in ZG is effectively random. There is no preference to one value or the other. There is no shape, completely random. What gives you random physics? Hadronization and non-perturbative structure, right? You can look at what is the angle corresponding to this third split. And it's all within more or less 0.1, 0.15, so very, very, very narrow. This is where we start to hit our calorimeter resolution in the size, right? That's why tracks are very important for these measurements. So we can see an evolution in our jet, where the first split works perturbatively, the second and the third have a hard time, and this naturally defines a time axis. So this is a three-dimensional measurement, right? So this one is a two-dimension. It has the momentum and the ZG. So now we have the ZG, the momentum, and the split number. So this is unfolded or corrected for detector effects in 3 dimensions. I am again not satisfied. I want to go to many dimensions because my jets look different, right? They have a significant variation in their topology, and I want to quantify it. I want to know what a jet looks like. So this is a new measurement that we did that was just released last month at DNP, which is the US conference by a graduate student, Yao-Chi, who works with me when I was at Yale. So what we did here is we unfolded 6 dimensions of our jet simultaneously. What are those dimensions? The jet PT, the jet charge. The charge is defined as a fractional weighted sum of all the charge of the particles inside the jet. So the charge includes the electric charge. So it's one-dimensional more because the full momentum doesn't care about the charge of the particle, right? So here we go. This is an extra dimension that I can tell you before. Charge, the mass, which is the full momentum norm, the ZG you already met, the RG, and once you do the grooming, you can get a groomed mass. You can essentially, it's a smaller mass. So what we show here, once we unfold that in 6 dimensions, we can effectively start slicing and dicing in a much larger phase space and uniquely identify populations of jets, right? So here, the y-axis is the mass of the jet, the x-axis is the charge of the jet, and the z-axis effectively is a probability. So it's the number of jets found in a particular selection. And these are plotted for 20 to 30 GeV jets in 200 GeV proton-proton collisions. So what you see here is something very exciting, right? If I ask for a jet that has a large mass, you are more or less going to get a jet that has a charge closer to 0. Okay, let's intuitively see why this is the case. What is the electric charge of a gluon? 0, right? Good. At least we're there. Good. So if my jet starts with a gluon, I cannot create charges willy-nilly. I have to conserve electric charge. So if I somehow recover all the particles, I don't do that, of course, it's a small jet. But let's, for the sake of argument, let's say that the bulk of the jet is within my jet, right? If I sum up all the charges, I should get closer to 0, right? Gluon jets, in addition to quark jets, they have the larger cover factor, they have the larger radiation, they can do glue to glue-glue, or glue to QQ bar. So they typically tend to have wider jets. Wider jets mean larger mass because you're adding full momentum quantities, right? So larger mass, smaller charge, you end up selecting gluon jets with the same PT, with the same R, right? So if you go to smaller mass now, then you go to either side. So if you go to this side, you are selecting potentially up quark jets. If you go to this side, you're maybe selecting down quark jets. This is not a star collaboration talk, which is why I can say this. If this is a star collaboration talk, we will just say you can select, you're more sensitive to quarks. So now we know the whole story, right? That's where we end up with this part that different jets are different. You need to know in a multi-dimensional phase space what your jet looks like, right? So it's also important to quantify the time. So I talked about, in this case, there is a natural time axis. So this is a very, very new thing, essentially started by Liliana here and other people, where you can define, using your kinematics, a formation time of the jet at a given splitting, right? And here you can see in vacuum here in PP, this is the blue curve, and in the quenched example, this is the green curve. All you need to know is that you have more jets that survive in your heavy ion case with a larger formation time. So they go essentially outside of the medium in a sense. It's not completely true, but for the sake of argument, we can take that, right? So measuring this can give you a useful handle in these jet quenching studies. Okay, so from there, when we go to the differential energy loss, how am I doing on time? So I'm like halfway, perfect. So I have 29 slides, so we're doing very well on time. So this is a phase space that I want to spend some time. I really like this. If you have seen it, she has seen this probably 10 times. But if you have seen me give a talk in the last 3 years, you have seen this slide. Right? Since you're all mostly new, I'll explain it. So we have this emission, right? This is where I also like this board. Right, so this is a quark. Let's say it radiates a gluon with a certain energy omega and a certain angle theta. I can calculate the formation time of this particular emission using simple QCD rules. So it's effectively 1 over theta squared times omega. There's some factors in there. We can put it in when we make the plot. Right? So just focus on the black curves. The y-axis is the formation time. The x-axis is the energy of the emitted gluon right here. Each of these lines, these black lines, correspond to a different opening angle of the emission, right? So if I fix a certain energy and I ask for when that emission happens, the wide angle emission happens earlier, the narrow emission happens later. So that's what we already know from QC, right? For these red lines, they are effectively a parameterized radiation due to the plasma, right? There's this Q hat, a parameter that's effectively the average energy loss per distance traversed in the medium, right? So if I vary the value of Q hat, I can extract a medium-induced emission formation time, right? That's this tau med, and that curve looks something like that for different values of Q hat. So you can see there is multiple phase spaces in this plot. If you're sitting right here, you're only sensitive to vacuum-like radiation, right? If you're sitting in the bottom corner, you're sensitive to both. You can see the medium modifying the structure. And if you're in this region, well, there's very, very, very wide angle vacuum, but you can also get different angle theta emission due to the plasma. So for the students, just to give you a scale, let's think about units. So this is Fermi over C, right? Fermi is 10 to the minus 15. Speed of light is 10 to the 8. So 10 to the minus 15 divided by 3 times 10 to the 8 is something like 3 times 10 to the minus 24. So seconds, 3 times 10 to the minus 24 seconds. I'm waiting to see your heads being blown, right? That is the scale in which we are studying this physics now. Parton dynamics in multiple units of 10 to the minus 23, right? Okay. So when we want an observable that we can actually measure in heavy ion collisions, we have to do one thing. We can't just go willy-nilly do it. Okay, a lot of people did it. That's useful. We saw them struggle and fail, but we need to learn better from them, right? If I have a jet in proton-proton collisions that looks like that, if I take the same jet and I put it in a heavy ion collision, there is so much background. So for the Atlas people, you have pilot, right? If you have 200 vertices, you get lots of pilot in your jet, but they're all from different vertex. Now imagine that 200 pilot all coming from your primary vertex. There's no way to distinguish these red guys versus the jet. So these is what we call uncorrelated background for a jet. And this background is not flat. This background is modulating. This background is fluctuating event by event. Because the plasma is a fluid, it's flowing. So if you go with the flow, you can get a high background. If you go against the flow, you end up in a trough, right? Very complicated, right? So whatever observable you measure, it better have a diagonal correlation. If not, what you're measuring is the impact of this background. You're not measuring physics. So this soft drop observable that I told you, that I praised so much in the beginning of the talk, well, that doesn't work in heavy ion collisions. In PP, it's great. It tells us everything we need to know about our jet. But in heavy ions, here's the value of this RG in PP. Here is it once I put in a heavy ion background. There's some diagonal, and then bang. We have this off-diagonal cancer in our plot. You cannot cut it out. You can cut it out if you go to some very funny places where you do very hard grooming and you go to some regime where you very bias your jets, right? But this doesn't tell us that if I select on a large opening angle, which is what I want to do according to this, right? The large opening angle is where the medium diffuse emission is sitting. The large opening angle can correspond to any angle in PP, purely from background fluctuations. So this is where, again, Liliana comes to the rescue with one of her earlier papers that talks about subjets, right? So this is where we take our jet, we recluster. We don't look at the original clustering tree. We recluster with a certain smaller radius and extract these red and blue circles, and we define a z, which is the momentum fraction of the softer circle divided by the sum of the two. And theta is effectively the opening angle, right? For example, this is what the z and the theta look like. You saw the zg before, it was steeply falling. The z subjet, on the other hand, is rising. Because you're looking at objects inside the core of your jet. The momentum is shared. You're not looking at softer objects, you're looking at core, right? And effectively, the angle is more or less narrow, right? This subject is useful because it does not have a lot of off-diagonal elements. So you can go ahead and measure this in heavy ion collisions. You can cut on a jet opening angle, and you can say that you have selected wider jets or narrow jets. So that's what we did in STAR. Recently, we selected two different populations of jets. You don't need to know the details. I have this cartoon here where I mapped my two different populations. And using our estimate of the omega and the theta, we compared theta between 0.1 and 0.2, 0.2 and 0.3. You can extract the formation time for these two populations of jets. This is a differential study. They are sitting somewhere here. So what we found is that there's no significant difference in the signature of the energy loss. They are more or less the same. So this tells you that you need to go smaller. Your opening angle is not large enough. In this case, you need to go to either a larger momentum, or you need to go to wider angle in order to see the study, in order to see this effect. So that's what I have a student working with me now, doing this with the new SPX detector, right? So we are not the only ones. There are also measurements from Alice and Atlas. They measure different. They actually measure this RG because they are somehow still enamored by the soft drop. Can't really blame them. It's okay. It's a good measurement. They go to different grooming criterion. They have a specific subset of jets that they then study this, and they see different behavior. So both these plots, the x-axis is as sort of an angle. So look at the top x-axis here. So that's RG. This is a ratio. So ignore the bottom. Look at the top here and look at the bottom here. And you can also see the data more or less have a trend and then a different trend. So falling, difference. And that difference happens roughly less than 0.1, right? Here, less than 0.1, there is a rising trend in the data, there is a falling trend in the data. So something is happening at 0.1. We don't know what exactly. What might be happening is a transition from coherent energy loss to decoherent energy loss, but we cannot say it yet, right? We have to prove it. This is effectively where we are going next in the US. So the 2015 long-range plan effectively has ended. So 2022, we are now in the process of writing a new long-range plan. I'm one of the people writing the sections on jet substructure. So you can see my thoughts and opinions will be reflected in the in the long-range plan. What we right now have is a potential limit on the upper value of the coherence length. So this is a use case of a very powerful differential measure, right? That tells you something physics-wise about the plasma. In this case, a coherence length, right? So we are done with what we are now. Essentially where we are going next. So this is the completion of the RHIC scientific mission. RHIC will stop running 2025. So 3 runs left, 22, 23, 23, 24, 25. And then RHIC will shut down. We are trying to push it to 26, but then you always push, right? So what do we have next? We have, before we go there, any questions on part 1? So all very clear. Good. You're all experts. You can actually write the long-range plan with me now. That's how skilled you are. So now we have in STAR, we have some upgrades to the inner time projection chamber. We also installed a new forward upgrade that has, here you can see 3 layers of silicon, 4 layers of gems. We have an electromagnetic calorimeter and a hadronic calorimeter, so we can do full jet reconstruction in the forward direction, which is super exciting because you can tag events that have a forward jet and study the mid-rapidity activity, which we have never done at RHIC before, right? There's a new detector at RHIC, which is the S-Phoenix detector that builds LHC style capabilities. It has an inner vertex tracker. There's a very fast TPC. And also mid-rapidity ECAL and HCAL. So STAR only has a mid-rapidity electromagnetic calorimeter. So our energy scale is off by quite a bit, right? So there is a lot of debate within the community where we are going to go. There are a lot of things we can do. We can measure the inclusive, or we can measure heavy flavor energy loss. We can look at different Lund planes or different topology. There's also this thing about the energy-energy correlators, which there's a lot of hype, and I am sorry to say participating in the hype. And so is Liliana. We managed to convince her. So what we get in S-Phoenix is a lot of statistics to finish the mission, right? We're going to collect effectively at 40 GeV at RHIC. We expect to have, these are jets, we expect to have something on the order of 20 to 30,000 40 GeV jets, which is crazy, right? At least at RHIC. That level of statistical precision will allow you to go everywhere in the phase space, right? We also have direct photons and good enough statistics. And then here you can see we can also look at, once we have the photon, we can look at the delta phi. And the photon is a cleaning probe because the photon doesn't interact with the plasma. Okay, the photon is an electrical neutral object. The QGP has color. Photons do not interact with color unless if they radiated QQ bar pair, then they interact, but we'll forget that, right? So the photon, we can look at it back-to-back with a jet via contrast scattering, and we can say either they're deflected or not. That tells you something about the quasi-particle nature, right? Something like a very simple Rutherford scattering, but in the plasma. With the large kinematics range, we can also go to forward jet from RHIC. So this is a new paper from Danny and Alba that was on the archive last month. So this looks at the KT. I already explained the KT to you guys before. Each color corresponds to a different rapidity. So the red color corresponds to forward rapidity, the blue is mid rapidity, and this is effectively how different these distributions are, right? Because as you vary the rapidity of your jet, you're also varying the quark and gluon fraction. Mid rapidity is more quarks, forward rapidity is more, mid rapidity is more gluons, forward rapidity is more quarks. So you have a different handle on your jet measurement. That's the whole idea. We know jets are different. How can we systematically study them, right? With the higher statistics, we can also bridge the gap between what we measure at this is the CMS measurement at large angle as a function of PT. This is the Atlas old measurement. This is the Alice new measurement. There seems to be some tension between them. S-Phoenix is built to collect jets in this range and effectively solve the tension. So this is the last couple of slides about the correlators. is effectively studying the opening angle between charged particles in your jets. And this comes from a conformal theory perspective that you can actually define regions in these two-point energy correlators that are sensitive to perturbative effects and that are sensitive to non-perturbative effects. So this is a very new area of study. You can see the papers there. The vacuum baseline looks something like that. This is as a function of the angle. The emission is effectively log, right? So here you have a log scale, so it's a straight line. That's your vacuum emission. Any medium-induced radiation has this kind of peak-like structure. So you can quantify the onset opening angle, the peak opening angle. Each of these colors correspond to a different Q hat. That's the interaction with the medium. You can then extract this ratio, this onset divided by peak, as a function of the jet energy, and you can see a clear deviation in the trend. This is again an example of coherent versus decoherent energy loss inside your plasma, and this goes to the point of the second part of our physics, which is that you can then study exactly how the medium impacts your jet. So, last part of our talk is we are going to look ahead to the EIC. I have not said EIC in more than 40 minutes, so now you're going to get it. So here's the jet PT. Why do I talk about RHIC a lot, right? Because jets at RHIC are a natural precursor to jets at the EIC. They are almost similar kinematics, right? So here's the Pythia production of deep inelastic scattering. That's what happens at the electron-proton collisions, right? You can study roughly, 5 to 30 GeV at the EIC, more or less the same at RHIC. So jets that you measure now are an effective baseline for what you're going to do at the EIC. But the caveat that the EIC is a cleaner environment. There's no multi-particle interaction. There's no initial state radiation from the electron. The quark can still do something, but what you measure is what is happening. Right? Almost very, very clear. So there's a lot of measurements, there's a lot of theoretical prediction about what might happen to your jets. This is the Rutherford scattering of the jet and the electron. This is the RG opening angle. Each of these lines correspond to a different cold nuclear matter effects, right? You can see there's some differences that you can potentially measure. This is the energy loss calculation using different PDFs that tells you about the cold nuclear matter effect. This says we should expect some amount of energy loss of the jet going through the nucleus, right? So there is promise to definitely do this. So the last part of my talk, I want to talk about hadronization. So this is one of the millennium problems. I am not going to sit down and calculate and solve this, but I can do a measurement that points someone to an interesting space where they can go ahead and solve this, and then we share the prize later, right? So here, as a function of this formation time in Fermi over C, there's some recent work by George Sturman, Yenting, and others. George Sturman is one of the very original jet people, 1979. So he and Feynman have this paper that talks about QCD jets, right? So this is the RC observable, which is effectively the number of light sign, so electric charge, number of light sign particles minus number of unlike sign. So if you have pions, how many positive pions versus how many negative pions as a pair versus number of positive and negative pairs together, right? Divided by the total. And here you can see this is the calculation from Pythia and Herwig. Each of these is a different species of ions, kaons, and protons. For protons, both the models more or less agree in this region. But if you go to the transition region, there's significant difference between Pythia and Herwig for pions and kaons, right? The value of RC being -1. If you have more unlike sign, that means you have string breaking, right? If you break a string, you end up with a positive and a negative on both sides, right? If your RC is 0, well, that means you're completely random. You don't have like sign, you don't have unlike sign. You kind of have the same, right? So even in here, as a function of formation time, you can select 3 different regimes. You can see there's potential interest in this transition region. Last but not the least, so this is the plot from Nuno's master's thesis that he just defended very nicely yesterday. And this will be shown in an upcoming paper, where what we are looking at as a function of this formation time is the two leading particles in your jet, the high energy particles, right? Charged particles. If they are the same charge, in this case, both blue colors, right? Equal charges, you take a ratio with the total distribution. So effectively, the sum of these two is 1, right? The red one means that they are opposite charges. So this plot is at RHIC, this is at the LHC. What you see is there is a gradual separation that maximizes at some formation time, maybe around here, there you see way more opposite charges than like charges. I mean, this is obvious. You do have to have string breaking at some level. But if you don't assume string breaking, this is not obvious, right? If you go to the LHC, you see a very unique population of jets that are very early formation time, where you will produce as many like charges as unlike charges. So what is happening for these jets with respect to hadronization? How is it different in this regime versus this regime? Completely unknown. So Nuno's thesis is going to have lots of big ramifications that he maybe doesn't know yet, but we will definitely see it. So that's my conclusion. There are 3 parts of the story. The goal is to tag, exploit, measure different parts of the jet that tell us something about fundamental physicity and non-perturbative dynamics. We are right now laying the groundwork for discovery physics at the EIC. But before we go there, we have to finish the RHIC mission, which is understand how energy loss happens. That's where we get to pedagogical, which is learn how different jets are arranged differently. So that's all I have. Thank you very much.